Yes, thanks for the introduction. So my name is Sprenger. I'm a PhD student at the Saarland University and working as a researcher at the DFKI. One of my main projects is the MOSEN project, where we investigate modular simulations of natural human postures. And this is where I know Felix Gaisbauer from, who is the first author of the paper and is actually working as a researcher at Daimler. And unfortunately he couldn't make it today, so I'm stepping in for him. Yes, our paper is on motion blending, which is usually used for keyframe animations, where you take the start and the end keyframe and try to interpolate the in-between frames for a given time frame, basically. In addition, obviously, I have to reconstruct the global translation in order to get the whole animation walking in space. But the problem is that this is a very time-intensive process, and if you are not an artist, like I am, your animation will probably suck and not look very natural. Fortunately, there is a large set of data, motion capture data, and we saw one data set earlier. This one is maybe more famous. It's the CMU data set, quite old but very well researched. It's about 2,500 motion files for 6 categories, with a large variety of postures and durations. So we thought, okay, can we use this data to actually do something more interesting for motion blending, so that at least the in-between frames are more natural than the keyframes. And we did this by constructing a fully connected neural network, which takes in the start posture and the end posture and a blending weight, and should produce a natural in-between frame at this specific blending weight. We used a genetic algorithm to construct to define the hyperparameters of the network, and this genetic algorithm told us that 3 hidden layers, 512 hidden units would be best, using scaled exponential linear units as the activation function, and an optimizer, and additionally we improved on using 2 training phases, so one for actually training the network using 32 batch size, and then another one using a way larger batch size to kind of fine-tune the network and keep any bias out of the network. We represented our motion on a kinematic skeleton, retargeted to the Unity mechanism system with 21 joints. And we used local rotations, but not as angles, Euler angles or quaternions, but as a 6D representation. And basically this one attaches 2 Cartesian vectors to each joint. So one vector kind of goes along the bone from the joint to the child joint, and then the other vector is kind of orthogonal to that. And with these 2 vectors, I can basically describe any rotation of the joint in space. And I still have the benefits of using Cartesian vectors rather than Euler angles, which our experiments and some of the latest research has shown to be superior when using neural networks. We additionally normalized the clips to the root position and the root rotation. So basically all of the vectors are local to the kind of root position, so my projected tip position and my forward-facing direction. And obviously then I need to encode both as well to the network in order to get the full animation out of it. So in total, again, our network takes in the start and the end, takes in the blending weight, and produces a blended figure. We used the CMU data, split it into training and testing and validation, performed some random, sampled some random cuts from the animation clips between a tenth of a second and a full second, and then normalized as well the blending weights to be between 0 and 1, just to be consistent. Additionally, we tried to improve the results with some post-processing steps. So besides the actual network prediction, we still performed some linear blending. We didn't directly use it, but blended the blended result with our network result. The reason was that our network sometimes produced some discontinuities, most of all in the start and at the end. So by using this U-shaped blending weights, we could remove these discontinuities and still keep the in-between frames quite natural. And then, quite a usual thing to do is kind of ground the motion to the ground plane so that it's not floating above the plane, but it's actually positioned on the ground. Yeah, here you can see some of the results. So on the left, there's the interpolated one, just using pure linear interpolation. In the middle, there's the original motion capture data, and on the right, there's our result. And as you can see, our network has learned quite some semantics of the motion, most of all stepping, which is the problem for linear blending, because then if you have the start and the end being quite similar from the feed, like kind of sliding over the ground, our network can produce natural stepping motions, which is quite great in my opinion. But we did some numerical evaluations as well. So first of all, we looked at the end effectors, so hands and feet, and how accurately we could interpolate them comparing to the ground truth. Most interestingly, we did not improve really on the linear interpolation on average, but we didn't make it worse either. So the positional error is approximately the same. We compared it for different interpolation weights as well. And here you can see kind of the differential error between our approach and linear blending, which is about 0, so there's not really a difference between the positional and effector error. Then we thought, well, another thing we could do is look at the self-collisions. So in animation, I can collide on body, and the animation can kind of go through my body, most of all with arms and feet, this happens. And this is kind of bad because it's unnatural. So we constructed such a box collider figure, calculated the number of collisions, and obviously we did not use any motion capture data for this validation step, which already had some collisions inside, so the best thing would be that we don't produce any collisions. In this case, we could improve on linear blending quite a lot, so we got 25% less self-collisions than compared to linear blending, which again is kind of a numerical sign that our approach produces more natural combinations. Obviously, this approach has some limitations. So, first of all, we did not include any animation time, so this purely interpolates 2 frames between 0 and 1. So it does not test any concept of time. It does not include any kind of joint velocities or acceleration as well. And we did not use any prior knowledge of this UMU dataset, so no labeling information other than the motion capture data itself. And this sometimes can produce some errors. So for example, here you see a reaching motion, and the right foot is kind of moving forward. So this could be as well quite similar to the actual start of a gate cycle. And the network kind of seems to assume the same, because it starts moving the right leg to do the walking, but then the animation goes back and stays with the foot on the ground. So this probably is because of the missing information about the animation time, so that it doesn't really know how much time it's actually going to interpolate and how fast this animation is actually. Other things besides integrating this in such an approach we want to do is look at the decomposition in body parts. So for example, landing the upper body independent of the lower body. And I mean, obviously it makes sense to combine this with a kind of adversarial network and a game-like approach to improve the naturalness of the resulting motion. So in summary, we constructed a deep posture blending network, which does not harm the end effector error, so it's very similar in the error compared to linear blending, but reduces the self-collisions and thus produces more natural in-between frames than linear blending. Thanks for your attention. Any questions I can answer?
Feel free to ask questions. Yes.
Maybe I'll just talk. Okay. Did you conduct any user studies? Because of course that's. Did you conduct any user studies? Because that's a good way, of course, to test how natural motion is.
No, unfortunately, we did not conduct any user study. We looked at the motion data ourselves, which is not a real user study for sure. But yes, this would be necessary if we are going forward to actually look at how people perceive this and whether it's more natural if they look at it.
We have time for more questions, so don't hesitate, don't be shy. Yes.
Hi. Just a clarification on your comment on end effector error. You say it didn't really improve over linear blending, but it seems something like the stepping motion you showed should be a greater improvement compared to the motion capture. I'm just wondering, that seems a bit odd to me that you're not seeing improvements.
Yes, this is most of all an artifact of the CMU dataset, that it's very containing a lot of variations in the motion. And I mean, for stepping motions, linear blending really performs poorly. But if I, for example, reaching a pointing motion, then linear blending is actually quite fine with respect to the anti-effector error, because this is usually a linear motion anyways. So this is mostly an artifact of the dataset we use, that there are so many animations where linear blending is already quite good that we could not improve on the anti-effector error there. Just looking at the walking animation would probably have improved the interpolation anti-effector error, but not for the whole variety of motions.
Right, fair enough.
So we have time for one more question.
All right, I'll just pause. Did you think about using some MIG to fix some of the end-effector stuff? So for the feet, for an example, in that example, there was like some feet floating. I don't know if you wanted to maybe block the feet.
I was told that we use final IK for actually grounding the animation to the floor. I personally did not look at this step specifically. Yes, IK would be a solution to do this, but I mean, if you just consider blending, then probably it's not good to kind of do too much post-processing then anyways. But yeah, obviously, full IK, for example, is always a good thing. But then considering a lot of variation in motion, if you don't have stepping motions, then full IK might not be a good thing. We had, for example, some animations where there were swinging animations where usually you don't really know where is the IK target anyways.
Let's start again the speaker.